on this last day, but not the least day. We're up for a series of very nice talks this morning, I think, starting with Sylvie Corteel. Sebastian has started this trend to say that people have done a tour of a country during their career, whereas Sylvie was just telling me she's done a tour of Paris and its region during her career. And now she's directrice de recherche in Paris 7, which probably is not called Paris 7, but yeah, Université Paris-Cité. And she is also sometimes in Berkeley, nothing less. It's a pleasure to have her here. Thanks a lot, Sylvie, for coming. And today she's going to talk about the lecture hall graphs and the Askey scheme. Thanks a lot.
Okay, so good morning, everybody. So I was planning to talk about something else, so that's not the abstract I sent. Okay, I was planning to talk about tilings with lots of pictures, like more Friday morning talk style. But finally, everybody last night was saying like, oh yeah, flageolet, flageolet, flageolet. And what I'm going to tell you today, even though it's going to be really hidden, is all due to Philippe Flageolet. Okay, so I'm going to talk about some things that we are currently doing with, I guess, also two people in the UK, Bhargavi Jonadula and John Keating. And this started when I gave a talk in Berkeley that actually was remote. And Bhargavi was attending from Oxford. And we started together thanks to this COVID life. So finally, COVID is not bad for everything. It made us work together. And this is also joint work with John Kim. Okay. And so this whole field, okay, of studying the combinatorics of orthogonal polynomial is all coming from this one paper due to Philippe Flageolet that's called Combinatorial Aspect of Continued Fractions. Okay, so today I'm not going to talk about continued fractions. But finally, what's behind all what I'm talking is this continued fraction coming from orthogonal polynomials. And it's really this seminal work of Philippe Flageolet that started that. Okay, so he had given combinatorial interpretation for coefficients of certain polynomials using this idea of continued fraction and certain Motzkin paths that we're going to see later. Okay. So I guess this is my thank you to Philippe Flageolet. Okay, so I really like working with orthogonal polynomial, and it's really him who brought that to combinatorics. Okay, so here is the outline of my talk. So I don't know, I skipped the time. Oh, here's the time. How much I'm going to say, but I'm going to introduce you what are orthogonal polynomials. I'm going to explain to you this connection between lecture hall partitions and a given family of orthogonal polynomials that we did with Jiangsu a few years ago. And we're going to introduce this lecture hall graph. And what we're going to see is finally that this idea we had for little q Jacobi polynomial works for the whole Askey scheme. Okay, so I'll give you the example of Askey-Wilson polynomial. But finally, looking at weighted paths on this lecture hall graph can give us combinatorial models, both for the moments and the coefficients of the polynomials. And I'm going to explain why this is kind of better than the model using Motzkin path. It's because after, even though I'm not going to talk about that today, we can go to the multivariate orthogonal polynomial. And at the end, I guess as it's people doing more asymptotics and analytic combinatorics, I'll try to talk a bit about some asymptotic results that we've done with David Keating and Matthew Nicoletti. Okay. So I'm going to look at a sequence. So Pn of x, okay. So n is an integer greater or equal to 0. X is my just variable. And I'm going to call that an orthogonal polynomial sequence. So n will be the degree of my polynomial. Most of the time, my polynomial is going to be monic. Okay. And I have a linear functional that tells me that if I take the linear functional of two polynomials, Pn and Pm, It's always going to be 0 if n is equal to m, and non-zero if they're equal, and then I can come with a coefficient. Okay. So as we're going to see, there's many polynomials that are orthogonal, and all the classical ones are now classified. But here is a very simple example coming from this integral. Okay, and we can see cos n theta as a polynomial in n theta. Okay, and if I define by Tn of x as Tn of cos theta is cos n theta, I get a family of orthogonal polynomial of degree n. Okay. So, but today I'm going to do mostly combinatorics. And one of the things we care in combinatorics is once we have this linear functional, okay, we define it on polynomials. And so once we know how to apply this linear functional to just x to the n, we can do it on any polynomial. Okay, so that's what we call the nth moment of this linear functional. This is mu n is L applied to just the monomial x to the n. Okay, and so what Flageolet showed, and many others after, is that the moments of some classical orthogonal polynomials have always nice combinatorics. So if I take the Hermite polynomials, what I'm going to find is going to find the number of perfect matchings, or the number of involutions with no fixed points. If I look at the Charlier polynomials, I'm going to find set partitions. Okay, so I take my set and I partition it into disjoint subsets whose union is the set. And then when we find Laguerre polynomials, okay, the moments are the number of permutations of 1, 2, up to n. Okay, and then we can continue like that, take the whole set, okay, and there's very cool combinatorics. And since the 80s, a lot of people, including me, have studied these combinatorics of moments of orthogonal polynomials. So, but something that's known too is that whenever you have a linear functional, your polynomial must satisfy a three-term recurrence, okay? So you're gonna get two sequences, Bn and lambda n, okay, for n greater or equal to 0, and lambda n cannot be equal to 0. And if you have a linear functional, that means you will have these sequences Bn and lambda n, and the polynomials will always satisfy this recurrence. Pn plus 1 of x is x minus Bn Pn of x minus lambda n Pn minus 1. Okay, so you're really constrained in a type of polynomials you can build. Okay, so here I give the examples for the three families that Hermite, that was giving us the perfect matching, the set partitions, and the permutations. But in this talk, I'm also interested in what we call the mixed moments and the coefficients, not only the linear functional of x to the n, okay, but I like to be able to write, okay, my polynomial in the classical basis, so compute the coefficients of my polynomial, but also to do a change of basis and express x to the n in the basis of my polynomial, okay? So the sigma nk are what we call the mixed moments. If k equals 0, I just get mu n again, because sigma nk can be defined like that. It's the linear functional of x to the n pk divided by the linear functional of pk squared, okay? And then the coefficients, okay? So, and I like to find a combinatorial model that both gives me the sigma nk and mu nk at the same time. And so, as I said before, my model that I want to build, I want it also to work in the multivariate orthogonal setting, okay? Because I can now, if I know a family of orthogonal polynomials, okay, I can build a multivariate version, okay, by doing a ratio of two determinants that I build from my family of one variable orthogonal polynomial. Okay, and it's going to give me a symmetric polynomial, so a polynomial that's symmetric in all the variables. Okay, and that's going to be orthogonal. Okay, so that's the classical result. So if I start from a one variable family of polynomial and they're orthogonal, if I do this, I take this ratio of two determinants. Okay, I get a family of multivariate orthogonal polynomials. Okay, and so for people who do algebraic combinatorics, okay, we are always obsessed with a Schur function, and that's the simplest thing you can do like that. Okay, I take the basis x to the m, and I compute this ratio of two determinants, and that's what gives me, I guess, if I fix the number of variables to be just n, the Schur polynomial. Okay. Yeah.
Have you defined multivariate orthogonal polynomials? Are they just the same as the univariate case, but now it should be orthogonal to all the ones with the smaller degree?
So, so the measure now is going to be the product of the measure plus some terms, some. So it could be many things, yeah. So we can talk maybe after. Okay, and so now that we have these multivariate polynomials, okay, what we'd like to do is to generalize what we've done here. Okay, look at the expansion in the base p or in the base x to the k. But now generalize where we want now to expand our Schur polynomial in the p basis or a p polynomial in a Schur basis. Okay. And then actually what we prove with Zhongsu is that now to do that, to compute these coefficients, again, it's like Jacobi-Trudy type argument. You just have to compute the determinants of these mixed moments and mixed coefficients. Okay. So that's the goal of my talk today. Okay. Can I build a combinatorial model for this sigma nk and nu nk for this Askey scheme such that I'm going to have combinatorial model for also my multivariate version? Okay. And so what does it mean to do that? Okay, what does it mean to have a good combinatorial model that can generalize to the multivariate setting? It means as we want to compute determinants, okay, we'd like to be able to build a model so that if I have, for example, a path model for sigma nk and nu nk, okay, that will give me a non-intersecting path model for the multivariate version. So why is that true? Why when we do one path model for the one variable version to non-intersecting path model for the multivariate version? Oops, okay. So that's, okay, I'm not there yet. So or maybe I'll just, okay. So because we have this very famous now in enumerative combinatorics lemma, the Lindström-Gesell-Vienno lemma, okay? So maybe many of you have seen that before, but if you haven't, I guess that's there's a very nice explanation in that proofs from the book. Okay, so if I have a graph that has a set of vertex and a set of edges, okay, it can be weighted, directed graph, but it has to be acyclic. Okay, I fix n starting points and n ending points. So I choose two sets of points. And the claim is that the determinants, okay, is the sum on all the vertex disjoint point system that start in A and end in B. Okay, so they can never share a vertex. And sometimes they come with a sign. okay, depending on the weight of the graph and things like that. But when the graph works well, okay, the only ones that survive are usually the ones that go from AI to BI, and where the path do not, if the graph is planar, for example, we don't have any sign, we straightly have positivity, okay? So that's what we want to find, okay, a graph that will be planar, that may be weighted, and so that when we go from the one variable to the multivariable setting, we just get that for free using the Lindström-Gesell-Vienno lemma. Okay, so now here is the Askey scheme, okay? So I talked about a couple of them. Actually, this is the Q Askey scheme. So where things are hypergeometric with a parameter Q. So I had talked about Charlier and Hermite and Laguerre, and they all have a Q version, okay? So we'd like to build, okay, some kind of combinatorial model so that we can understand this whole scheme. Okay. So as I said before, this is all from Flageolet, and what they showed using this idea of continued fraction is that if you want to count the moments, mu(n), it's going to be a sum on some Motzkin path with a certain weight, okay? So a Motzkin path is a path that starts at 0, 0, ends at n0, and can go up, down, or east, okay? That never goes under the x-axis, okay? And then we're going to put some weight on the path. The weight is going to depend on the height here. So whenever I go east at a height k, I get a weight bk. And then when I go down, starting at height k, I get a weight lambda k, okay? So for example, we get the example for n equals to 3. So this path will have weight b0 times lambda, okay? The weight of the path is the product of the weight of all the steps, okay? So mu3 for general sequence, okay, we get b0 cube plus 2b0 lambda plus b1 lambda 1. Okay. And then if I put back my lambdas specific that I gave you before for Hermite, Charlier, and Laguerre, I could find back for example, n factorial, 3 factorial for Laguerre, okay? So to get 3 factorial, I don't remember what I have to do, but maybe all those are 1 and this one is equal to 3, and I get 6. So there's a general theory that tells you that for this one variable polynomial, okay, you can always get a nice combinatorial model. And then there's lots of nice bijection how to go from this label path to the combinatorial objects. So for example, if I look at Hermite, okay, so Bn is equal to 0. So I'm not going to have any horizontal step. And then lambda n is equal to n. Okay, so I get big path where the path at height n can be labeled 1, 2, 3 up to n. Okay, so here I have a path where height 2, so I can have a step labeled 1 and a step labeled 2. And it's easy to get a bijection from these Hermite histories to perfect matching. Okay, when I go up, I open an arc. When I go down, I close an arc. And then the numbers tell me how I can join the arcs together. Okay. Okay. And then we can generalize that to these mixed moments. Okay, so Vienno showed also in 83 that if you look now at paths that don't start at height 0 and end at height 0, but paths that start at a fixed height r and end at a fixed height S, okay, then this will give you some information also about the orthogonal polynomial. In particular, if R equal to 0, I get the mixed moments that I'm trying to explore. Okay. So that's what we want to study today, the sigma of NK. Okay, and I could have a combinatorial model like that from 0, 0 to NK. And that would give me my mixed moments. Okay. And then if I want to compute my new NK, so which are the other numbers that I want to study today, I have to see that as a generating function for some certain tilings called Favart tilings. Yes. Okay. But now I'd like to tell you why I don't want to use these Favart tilings or these Motzkin paths, is that they're not going to behave well when I want to go to multivariate settings. Okay. Because in particular, if I look at the underlying graph of a Motzkin path, this graph is not planar. And so when I'm going to compute determinants, my paths are going to be able to cross because the paths don't share vertices, but they can cross if the graph is not planar. And so I'm not going to be able to have positive result. I'd like to prove that my mixed moments are totally positive. And using this Motzkin path, I cannot do that. Okay, so that's our question here. So can we find a lattice path model for sigma of NK that will give nice non-uncertainty path model using Lex from and Vienna? Okay. So now I want to do my path on a planar graph. Okay, so that after, when I want to do the multivariate, I get positivity for. Okay, so that's the first thing we did in 2020, kind of maybe randomly. Okay, we studied that family of little q Jacobi polynomials. Okay, they're indexed by 3 parameters, A, B, and Q. Okay. And when Jiangsu visited me in Berkeley, actually, he had nice formulas for them. And I was just like, oh, I think I've seen these formulas before. Okay. And so what we could do is connect these combinatorial models using lecture hall partitions. So let me define to you what are these lecture hall partitions. Okay. So what's a partition? So a partition is just a sequence from the 1 to lambda k. It's a partition of n if they sum to n, and it's a non-increasing sequence. Okay. So for example, 4, 3, 1, 1, okay, is a partition of 9 because 4 plus 3 plus 1 plus 1, that's 9. Okay. So usually we draw partitions with a set of boxes. Okay. That here I chose to do 4, 3, and 1, and left justify it. Sometimes we wrote them from bottom to top or rotate them, but there's many ways of drawing partition, but basically each row or each column or each diagonal gives you information about the parts of the partition. Okay. So what's a lecture hall partition? So these were defined in 1997 by Bousquet-Melou and Erickson. So coming from a very different world, coming from Coxeter combinatorics. Okay, they count certain inversion in affine C-type, like in affine C-type permutations. But here I'm not going to explain that. Okay, so a lecture hall partition is like a partition, but on top we add some denominators. Okay, so we want to make it way more strict. So for example, here I draw my partition like that, 5, 3, 1. And it's a lecture hall partition because 5 over 3 is greater or equal to 3 over 2, which is greater or equal to 1 over 1. Okay, so we want partitions that are strict, okay, and more than strict because we have these denominators that come down. Okay, and so they were called lecture hall partition because kind of if you put the parts of the partition, okay, you can see that kind of as a lecture hall. Okay. this is made so that everybody can see down. And so what they could show is that it's not easy to prove, but the generating functions of these partitions is kind of as beautiful as you can get. It's just a nice product formula, product from I equals 1 to n of 1 over 1 minus q to the 2i minus 1. And so with Carla, we had also defined some similar things that are called planetarium compositions, where now we add also some divisors, okay, but the other order, okay? So these are composition, they don't have to be non-increasing, okay? Now we want to count sequences where alpha I over I is greater or equal to alpha I over I plus. And then again, if you compute the generating functions of these objects, okay, they have also a very nice product formula. So what we figured with Jiangsu is that finally, the mixed moments and the coefficients of these little q Jacobi polynomials, they can be seen as generating function of these objects, okay? So the moments, they are generating functions of planetarium compositions, okay, where now I want alpha 1 over k plus 1 to be greater to alpha 2 over k plus 2, etc. And then the u, v, and q follow some natural statistics on these objects. And what came for free is that now if we look at the moments like that, then the coefficients would be generating functions for strict lecture hall partition, okay? So, and also with some very natural parameters, okay? And so finally, we see really some kind of duality between this change of basis, okay, where now the moments are generating functions for these anti-lecture hall composition, and the coefficients are generating functions for strict lecture hall partition. Oh, in little q Jacobi. Oh, sorry. Like they're here. So, okay, so that's what we did, okay, and we thought that was kind of random, okay, that finally these little q Jacobi were just having a nice model coming from lecture hall partition, okay, but then Bhargavi, who has a lot of good ideas, wrote to us and said, I think this is not a coincidence, okay, I think you can do way more. Okay, so for example, now, so maybe you don't need to remember all my formulas, but so we did little q Jacobi that has 3 parameters A, B, and Q, and then Askey Wilson on top is a family where you have 5 parameters A, B, C, D, and Q. Okay, so these are the definitions for the Askey Wilson polynomial. So they depend on A, B, C, D, and Q. And you can rewrite them. You can write them as a hypergeometric notation, but here is the recurrence of these polynomials where things are a bit complicated, okay? Nevertheless, okay, for example, if it's not so clear from the definition, for example, these are symmetric in A, B, C, and D, okay. So I've been obsessed with those polynomials for quite a while, okay? And one reason is that they are a nice combinatorial model to study exclusion processes. So that's what we've shown, not only us, but we gave the combinatorial model that we can find the Askey-Wilson moments if we study the exclusion process with open boundaries. And so thanks to that, okay, we gave a combinatorial model for these moments of Askey-Wilson. Okay, so these are called the staircase tableau. So these are pretty complicated combinatorial objects where we have some like alpha, beta, gamma, delta inside. And then we have some rules on how to put the Q inside the tableau. And actually to find back the ABCD, we have this very weird change of variable. Okay, so we need to rescale and reparameterize. But finally, we are able to find some nice combinatorics coming from the SF, helping for the Askey-Wilson polynomial. So here is our motivation. Okay, can we find a lecture hall partition model for this Askey-Wilson, the same way we did for little q Jacobi? And for example, could they help us to give a combinatorial proof that these polynomials are symmetric in A, B, C, and D? Because typically here, when we do these change of variables and stuff, we lose this idea of symmetry. We still have some kind of symmetry between alpha and gamma and beta and delta, but these things are not symmetric in alpha, beta, delta, gamma. Okay. And then, so can we generalize what we did on Q little Jacobi to Askey-Wilson? And how can we do that to discover such a combinatorial model? Okay, so that's what we are going to use. Okay, we're going to use this lecture hall graph. Okay, so that's what we introduced with Zhongsu in 2020. So it's a planar graph. Okay, so it has all the vertices that are integer coefficients. And then in the ith column, okay, I add extra edges in each unit square. Okay, so I'm really building my lecture hall where we had like lambda n greater or equal to n. Lambda n over n will be greater or equal to lambda n minus 1 over n minus 1, greater or equal to lambda n minus 1 over n minus 3. So if I look at a path like that, okay, it's going to be exactly a lecture hall partition. And if I look at a path like that, okay, going from the top left to the bottom right, I'm going to get an anti-lecture hall composition. Okay, so finally, I'm going to get a model that's going to work both for my mixed moments and my coefficients of my polynomial. Okay. And so that's what's written here. Okay, so if I start at k infinity and end at n0, okay, what I'm going to get is exactly an anti-lecture hall composition that I want to do. Okay, and now what I want to look for is the correct weights on my steps so that I get exactly the moment. Okay, so here, so for example, the Q weight is going to be the simplest one. It's just going to be the number of cells under each step. Okay, but now I also have to look for more complicated weights for my A, B, C, and D. So that's how it works for the little q Jacobi. We find the correct weights to put on our lecture hall graph, and then we can get the combinatorial model. Okay, so here are the weights for the little q Jacobi mixed moments. Okay, so each step gets a nice monomial in A, Q, and B. Okay, and you can prove that the mixed moments are just these paths. Okay, and again, the weight of a path is just the product of the weights of the steps. And then the coefficients would be the path that start at k infinity and that start at n infinity and then at k0. Okay. And so what we did is we went just first one up in our Askey scheme, and we looked, can we do that for big Q Jacobi polynomials? Okay. And actually it works exactly as beautiful as before, except it's a bit more complicated. So before we had things that were just kind of repeat. Okay. So to go from one height to the next, I would just kind of repeat and increase Q. But now we're going to have things that have kind of bigger periods. So for example, here, I just put some C's. Here, I put some A's. Here, I put AC and AB and ABC. But I have some ways on how to build up my model. And again, we can find that the moments and the coefficients are just paths on these graphs with just monomial coefficients. Okay. And so in particular, as we get graphs that are sometimes have all weight positive. So here, if I put A to minus A, B to minus B, and C to minus C, and then change the sign here, then everything becomes positive. And in particular, I can show that this matrix is totally positive. And this says to me that if I want to expand this big Jacobi in a Schur polynomial, then I'm going to get positive coefficients. Okay, so in algebraic combinatorics, we love to have combinatorial interpretation of the expansion of a given family of symmetric polynomial in the Schur basis and to prove that things are Schur positive. And then you can do the same for Askey-Wilson, and again, it works. Okay, so it's a bit more complicated. Okay, so but we have some kind of guess technique on how to put these weights on this path. And now things have like period 8. Okay, but again, this works. You can find these nice weights, okay, that are just monomial. Just here at the beginning, there's something a bit more complicated here. But otherwise, everything is just a simple monomial at every step. Okay. So the whole theory follows, as I said before. Okay, the moments are the path from K infinity to N0. And the coefficients are the path from K0 to N infinity. Oh, so the path that go like that. Okay. So we can prove straight away that they are dual, okay, just by doing a very quick involution. And so I'm not going to give you the details because it's going to be, it would take me a while. It's a bit like a phone book. But it turns out that you can do that for the whole scheme. Okay, the whole scheme works this way. You can find lecture hall graphs that have fairly natural weights, okay, that are most of the time just monomial on every step, and the whole thing follows. So what we had done kind of randomly for little q Jacobi turns out that it works for the whole thing. Okay, so that's kind of the meta theorem. Okay. So it's not as nice maybe as the Vienna theory because we have to kind of find the weights for each family. So we still don't have the good explanation of why we can find such nice weights. Okay, but as we are on planar graphs, now we can get for free whenever a moment is positive, then the multivariate moments will also be positive. Okay. So anyway, I'm not going to give you any detail, but let me just tell you. So we have some kind of pumping lemmas, you know, on how when we understand what's going on at the bottom, okay, we have now a lecture hall graph model for these, okay, and we pump them to go up in a hierarchy, okay. So the proof is not always so hard. Somehow, once you start here, you have a way to pump all the way up and all the way up this way. And with this idea, we can generalize to all polynomials. So now the question could be, now that we know how to pump, you know, to start with a model and make it more with a bigger period, okay, could we go higher than that? But we don't know. Okay, so for example, these are periodic and we increase the period each time. And so we could continue this process and see what we get. I'm not going to talk about that, but that works too. Yes. Yes, and the way we guess actually is the most simple thing you can do. So I said that sigma nk is the path from k infinity to n0. So if I set k equal to n minus 1, okay, I just get a path from n minus 1 infinity to n0, okay? And this sigma n minus k gives me a series, okay? I sort its term in lexicographic order. I write them in a given lexicographic order that we choose. I write the terms like that, okay, in each column, okay, and magically it works, okay. So we know that it worked for sigma n minus 1 when we do that, doing that guess. But actually, once we choose a good order, it's going to work for any n and k. So like the simplest thing you could think about on how you put the weights on this graph, okay, kind of magically works in general. And then we can prove this just by induction. Okay, or maybe, okay. So that's the advantage of our lecture hall graphs. Okay, so whenever we have a model for a moment, we have a model for the coefficients too, because they're just paths on the same graph, just starting and ending at different points. Then whenever we have something positive, we can also, we can get the multivariate moments just using the Lindström-Gesell-Vienno lemma. We get a combinatorial model for that. And whenever the moments are positive, okay, we can prove that the matrices of moments that we get when we expand in a Schur expansion, okay, it will be totally positive. So this couldn't be done using the Motzkin path model. And the big surprise is that it works for the whole Askey scheme. Okay. So now, as we are in AofA, I'm going to try to tell you a little thing about asymptotics. Okay, just a couple of minutes. Okay, so when we worked on this little q Jacobi and when we defined this lecture hall graph, so I made a mistake. So I worked with David Keating and Matthew Nicoletti that were at Berkeley then. And now David is moving to Urbana-Champaign at that. And Matthew is coming back to Berkeley after his PhD at MIT. And we wanted to know how they behave paths on a graph. Okay, so I'm going to look at my lecture hall graph. I'm going to fix some starting points, fix some ending points, and try to make things grow and see how my family of non-intersecting paths is going to look. Okay, so that's the kind of question we asked ourselves in 2020. So, but now I don't have any weights on a graph. I'm just looking at paths that are just non-intersecting. So here is an example. So if I put my starting points to be all consecutive here, and my arrive point to be all consecutive here, and then I take a lot of paths, okay, that's what I get. So I fix a partition lambda, okay, that's going to fix where my path arrive, okay, and then the starting points are always going to be consecutive. Okay, so what we can see here is that we get a pretty nice asymptotic behavior. Okay, so for those of you who've seen this kind of talks, okay, what we call this type of asymptotic behavior is that we have two types of regions. Okay, a region that's liquid, okay, and a region that are frozen, okay, where the paths here, they don't exist at all. And here, the only thing they do is they go straight. Okay, so all the paths go straight. And then here, I can have this liquid region. Okay, and usually these two types of regions are separated by what we call an Arctic curve. Okay, that there's a sharp change of behavior between this and this. Okay, and one question you can ask yourself is if you fix a partition lambda, what will be the given Arctic curve coming from that? Okay, so for example, if lambda is Pn, 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 okay, so all my paths here are separated by P, but for a fixed P, we can prove using a more like a heuristic style. So I don't know if it's a proof, it's a physics proof, okay, that we get an algebraic curve of degree 2. Okay, but for example, for this partition here, Pn, Pn minus 1, so it would tell me that the paths are more spread out, the arrival paths are spread out here in the bottom. Okay, we could get an algebraic curve of degree P. But you can get also, depending on how you decide your arrival points are arrived. So if we spread them here and then have no arrival path, then spread them for a while, no arrival path, and then put them really dense and things like that. Depending on your partition, you can choose the arrival path to have very different behavior. Okay, you can see that this Arctic curve also will have some curves. Okay, so the top part will always be an algebraic curve. And here you can also compute these curves. So there's many techniques to compute these things. Okay, but the easiest one is what's been defined by Colomo and Sportiello, so which is not the most strong mathematically. It's just a heuristic. Okay, and it was proven to be really mathematically sound for one model, for the 6-vertex model by Amol Agarwal in 2019. Okay, so what's the philosophy? So you think that your model is having an Arctic curve, okay? And so, for example, this one here, it would be the semicircle. And what we are going to do is you're going to fix yourself far away. So it would be like, you know, my paths, they travel like that. And so now I'm going to fix the arrival of my ending path not to be there, but to be farther away from the others. Okay, so I'm pushing the end of my last path to be far away. And my hypothesis is that finally this path now, when it ends really far away, it can travel free and it's going to travel straight until it's going to hit the Arctic curve. And it's going to hit this curve tangentially. Okay. So I'm going to fix Z and R, okay? And I'm going to try to compute Z and S, sorry. And I'm going to try to compute the R, which is exactly the slope of my straight line here. And I think that this is going to hit my Arctic curve tangentially, okay? And so now I can vary Z or S or both, okay? And I get a whole parameterization of my curve because then now my tangent can just move around the curve, okay? And so when you do that, you can just compute these Arctic curves, okay, using this heuristic. But that works also for the cusp, okay? You can also, because I said the cusp were arriving when the arrival point were at a certain position here. And so you can use that same technique also to compute the equations of the cusp. So that's what we did with David and Matthew for this lecture hall model. Okay, for whole families of partition, we could manage to compute this Arctic curve. Okay. And so my open question is now that we can do the whole Askey scheme, okay, could I also understand the asymptotic behavior of the path system, but now using the weights that I add on these things? Because for now, we kind of did the easy version where the weights of the steps are all one, but now could we put these A, B, C, D, Q, and then depending on their values, see some different asymptotic behavior? A priori, the curves are going to move, but for now, I don't have a good way to compute that. So thank you very much. And let me just say that these are 3 or some young people who are looking for jobs. So if you want to hire people, Bhargavish is in the UK and David and Matthew are in the US. So feel free to hire them. Thank you.
So yes, so you mentioned that the previous combinatorial explanation was involving the ASEP model. So is it the case that you can get a kind of bijection between these 2 models and to your combinatorial explanations?
Probably, I haven't tried, but yeah, that's a good question.
Thank you. So if I remember well, usually in the Askey-Wilson scheme, you start from the top and then you use limits to go down.
Yeah.
And you're going the other way around. Does that mean that your top parameterization does not specialize well, or?
No, I think we could. I want to make sure I don't say anything stupid, but I think now that we know the result, we could go back down. Just when we did the guessing, we made some lemmas on how to go up. Because basically we take, somehow the idea is we take 1 level of the lecture hall graph and we make it in 2 levels, like we kind of double it. And so that's how we bump up. Like, so we have these infinite graphs, but we make copies of it and change the parameter.
I had a question, in fact. You said that one of your motivations was to understand, have a combinatorial proof of why it's symmetrical in A, B, C, D. Maybe I missed it, but can you explain now?
Oh, yeah.
Why it's symmetrical in A, B, C, D?
Yeah, I think I probably forgot about that.
Okay, well, I'm glad it's not me.
Oh, I don't know.
What was it? It's not super clear, is it?
So we do have a combinatorial proof now, but it's not clear on that. So
Okay.
yeah, I should have added a slide, and now I'm going to say something stupid if I try.
Okay, that's fine, that's fine.
But
Good.
thanks to this, we can prove combinatorially, yes,
You can
that it's
do it.
indeed
Cool.
yes.
Okay. Any more questions? May?
So for the ASAP, usually there are some boundary conditions involved. I don't see like how do they interact with lecture hall property here.
Also, for now, I have no idea how to relate the ASAP to the lecture hall property.
Okay. And when you say totally positive, do you mean totally positive or totally non-negative? Earlier in your
Probably totally non-negative.
okay. Okay. Yeah, thank you. It's very informative.
Oh. Silly. Yeah.
So do you have any idea about the asymptotic shape of the lecture hall graph or lecture hall graph? When you have a size growing, what would be some asymptotic shape? Does it follow from your study?
But the lecture hall graph is just, I define one thing and it just repeats over and over. So it's just something periodic, like the graph itself is fixed. But what I would like to understand is how the paths on this graph behave.
Okay. But you could take a uniform distribution on that and would it be relevant to wonder what is the asymptotic shape when you have an uniform distribution on lectural graphs?
Mhm. Yeah, that's something that would be interesting to do.
Mhm.
Any more questions? If not, let's thank Sylvie for the great talk.